today we'll be talking about how to extract and analyze data from OpenMM simulations. To begin with, I'd like to show you this slide again, which is a diagram of the various classes in OpenMM version 5.0. In the bottom left-hand corner here, these are all the different types of objects that you might read from files, such as the PDB file object, which you get from reading a PDB file, and the force field object, which you get from reading a force field XML file. This is some stuff you might already be familiar with. And the overall goal is to write a simple script in Python that will lead you to creation of the simulation object. And once you have the simulation object, it will allow you to minimize the energy of the system and do time steps in a molecular dynamics simulation and so on. Now today, we're going to be focusing on the right side of this, this chart, where the state object on your right contains all of the information that is actually that's contained in the current state of the simulation, such as where the atoms currently are. For example, you may have set the positions of the atoms at the start of the simulation, but after minimizing the energy, they might now be in a different position. And also other physical variables, such as the velocities of the atoms, the potential energy, and the forces can all be found inside this state object here. So as you can see, the state object is a component of the simulation object. Okay, the simulation object is in the middle there, and it creates this context object. So context is a part of simulation, and state is a part of context. And so basically the correct way to do this in a Python script is to look for the context object in this in the simulation, which then contains the state. Now, as you run the simulation, it's often useful to periodically get state information from a simulation, and that's what the reporters are for. Every simulation contains several what are called reporter objects. You can see them on the right side here. And reporters are functions that you can attach to the simulation object, which are called at a specified interval of time steps. For example, you might want to write out the coordinates in PDB format every 1,000 time steps or so in order to get what might look like a movie of your molecules moving around. So if you call this append method, okay, simulation.reporters.append in red up there, it adds a reporter function to your simulation. They are called at fixed time intervals, and they just they write information either to the terminal as you're running the simulation or to a file. And three types of reporters which we have implemented in OpenMM is the PDB reporter, which allows you to write coordinates to a PDB file. The DCD reporter, which does the same thing except for a binary format DCD file. And then the state data reporter, which prints out essential information about the state of your simulation. So in order to add a reporter, you need to have created the simulation object first, which we covered earlier in the tutorial. And you need to append these reporter objects that are highlighted in red. And as you can see, in order to create a reporter object, you need to pass it certain information. And here, the information is given by the name of the file that you want to write to, and also the interval in the number of time steps in order to call the reporter. So once you've appended these reporters to your simulation, then as you run the simulation, these functions will automatically be called and generate information for you. Now let's talk about the GetState method. The GetState method is the way for you to actually get to the state, which, if we remember correctly, is contained in the context, which is contained in the simulation. Now, the reason why GetState has these parentheses here is because this is actually a method on the context object. So when you call GetState, it actually creates a state object and gives it to you. And as I said already, this provides access to all physical variables. So after we've created the simulation object, going through these steps, okay, reading in the PDB file, the force field files, and I have PDB and force field objects, creating the system object by combining the force field and the PDB objects, adding an integrator and creating the simulation. Okay, now I can set the positions and to reasonable values, which are the PDB positions, and I can now get the state. Getting the state might be something as simple as this, where I call simulation.context.getState, and so a particular feature of the getState method is that you need to actually specify which physical quantities you want. And the reason for this, the reason why the physical quantities are not all just already there, is because they might actually be existing on the GPU and not in your computer's own memory. And to get them off of the GPU actually takes some effort. So that's why the getState method has options such as get positions, get energy, get forces, because in order to get every one of these variables, it actually takes some amount of effort. So we don't want to expend any effort that we don't need to expend. And once the state object is created, then you can get the potential energy from it using this get potential energy method. Okay, so what you finally get is probably going to be the energy of your system. So your protein from the PDB in the PDB positions, calculated using the amber 99 SB force field and the tip 3P water model here. Okay, I think this is probably the final slide in this presentation, where the goal of the exercise for you is to write a new reporter function. So as it turns out, these reporter functions are very simple. So we've decided to include as an exercise for you to write a custom reporter that might be useful for your own research. So the goal is that you might wish to observe a particular variable from your simulation as your simulation is running. The first step is to open the myreporter.py file, which contains the framework for a new reporter. So you actually just have to fill in a sense, fill in the blanks. So in the report method, the state object has already been provided for you. So you're able to get the different variables from the state, such as the positions, energies, and forces, and so on, and process them in such a way as befits your research project. So here, as an example, we are going to extract the position of the alpha carbon in angstroms from the state object and name it to a variable called output. Where if you look at your PDB file, you can probably identify the atom index of the alpha carbon. So just make sure to after getting your positions, make sure to get just the position of the alpha carbon atom, which is going to be one of the values in the list of positions. And then using methods that we outlined in this presentation, add the new reporter to the simulation using simulation.reporters.append in your exercise 1a.py, and you can direct the output to your screen by specifying stdout on your when you create the reporter object rather than the name of the file. And when you run the exercise, you'll be able to view your output, which is just going to periodically report on the position of the alpha carbon atom every 50 or 100 steps, depending on, or some other number, depending on what you chose when you created the reporter object. And then if you still have some time and you're interested in going further into this, you can try with more advanced variables, such as measuring the dihedral angle between four atoms. You can measure the phi or the chi angles for alanine dipeptide, for example, or the density of the system, which you can get from the total mass of the system and dividing by the volume. So with this, I think we're done with the presentation that explains how we extract physical variables from an OpenMM simulation. Thank you.